AP Chemistry, and welcome to Chapter 8, which again is mostly a review. That's the perk of this unit. There are a few new topics, and we'll spend a little more time talking about those here. Again, much of this comes from Chapter 10 from last year. So 6 and 7 came from Chapter 9 last year. 8 and 9 come from Chapter 10 from last year. If you just want a lower level refresher first, right, or just something to sort of help you in terms of filling out your picture and make sure you understand. Okay, so anyway, octet rule, which we talked about last year, right? So octet implying 8, obviously. Why is 8 the magic number? Right, 8's the magic number due to your S and P subshells being full, lending stability to an atom once those S and P subshells are full, because that's what composes the valence, right? Where the goal of every atom is to achieve a full valence. Note that that there is a little bit of flexibility there, right? As in every atom is striving for not striving, right? That's what I literally said in there. But every atom's goal is a full valence, right? That's why it reacts with other things. That's why it takes the electrons. That's why it gives the electrons or shares them, right? But that doesn't apply to everything, right? There are things that commonly have less than an octet. There are things that are capable of having an expanded octet, right? And there's that whole bunch of D and F block metals where the concept of valence gets a little bit of fuzzy, and so then the octet rule doesn't apply at all there, actually. So we'll have to use context and other data to help us make determinations there. Okay, so anyway, the three general broad types of bonding, metallic, ionic, and covalent. We get more in-depth in the next unit on metallic bonding and the types of solids that arise because of these things and the respective properties. But those are the three main types of bonding. We talked about ionic bonding back in Chapter 4, and here we just add some more detail to that. We talked about covalent bonding last year a lot, and again, all we're doing is adding some more detail to that. All right, so ionic compounds and lattice energy. Like I said in your outline, lattice energy, for whatever reason, does not have one clear definition. In your particular book, right, it's defined as the amount of energy what? Right, since it's positive, right, it's the amount of energy required to break apart, right, the amount of energy put in to separate solid ions into their gaseous ions, right? Note that other books, right, and even on the AP exam, it's often defined in the other direction, right, as in the energy required to, energy released when two gaseous ions come together to form an ionic solid. Obviously, you have enough knowledge to understand that if the values are positive, right, obviously it's the energy required to break. If the values are negative, right, it's the energy required to, or the energy upon energy released, right? So when you're discussing these, like in a free response or whatever, right, magnitude is a good word to employ, right? In that gets around the sign issue, right? If I want to talk about the magnitude of the lattice energy as being bigger or the magnitude of the lattice energy being smaller, right? That still gets to the amount of attraction, right? Without having to get bogged down in whether or not it's energy in or energy out. Okay, just something to think about. Over here we have the general crystal structure for sodium chloride. You don't have to know the specific crystal structures, like there are several different crystal structure types, but you do need to understand, right, that for every ion, right, it's surrounded by a whole bunch of other ions, which is then surrounded by a whole bunch of other ions, right, which leads to the properties that we see. And don't forget, even though we don't commonly encounter it in everyday life, right, there is no reason that an ionic solid cannot melt, okay? We can melt sodium chloride at high enough temperatures, right? And then at that point, it would be called molten sodium chloride, right? And it would be a free-flowing liquid, and at that point, it would conduct electricity, okay? A molten ionic compound would conduct electricity because we have flowing ions, right? Which is the same concept as when I take solid sodium chloride, right? Which does not have free-flowing ions because they're stuck in this crystal lattice, right? And if I dissolve it in water, we now have free-floating ions, right? So anyway, just tidbits you should be aware of. Lattice energies, to be mindful here, we're going to use our force of attraction, Coulomb's law, as always, because it's charged particles, right? And here, again, we always define Coulomb's law, right? We define our Q's and our distance for every new application. So previously, when we talked about it for atomic properties, we defined Q1 and Q2, right, as the protons and the valence electrons, and the distance between them, which sort of has to do with which shell you're talking about. Now, when we talk about Q1, Q2 here, we can talk about our cation And here we can talk about our anion's charge, right? And this would be the distance between those, which basically ties to what property? Right, this ties to radius, right? So things that have bigger radius, ions that have larger radii are going to have larger distances between my two charge centers, right? And smaller radii will lead to a smaller distance between my charge centers, right? Which then explains all the lattice energy trends that we see, right? So for example, if we're comparing our lithium series, right? As that anion gets bigger and bigger, right, and the distance between my two ions increases, the force of attraction goes down, the magnitude of the lattice energy decreases, yes, because there's a weaker force of attraction, right? Likewise, if we were to compare, where's a good point of reference? So if we were to compare lithium chloride with magnesium chloride, right, we'll see that those values are vastly different, right? Because here we have magnesium being 2, lithium is only 1, therefore, my Q doubled, which then makes sense that my force of attraction is significantly larger, yes? And note that your Qs are always more important than your distance, right? Your distance only changes marginally, whereas your Qs change in whole number multiples, right? It's either going to double or triple, right? Which is a far more significant impact, right? So you'll always look at Qs first, and if Qs are equivalent, then you'll look at the distance between them, right? So for example, here, if I'm going to compare magnesium chloride and strontium chloride, they're same charges, so then we'll look at our distance between them, right? Which would go back to the fact that strontium is larger again. Okay, make sense? All right, moving on, the Born-Haber cycle. Super duper important that you can read this diagram and understand it. So let's point out a couple of key things. Here, this one, right, that's the same heat of formation that we talked about back in chapter 5, where to form 1 mole of sodium chloride, I would form it from its constituent elements, and the amount of energy required or released is known as the heat of formation for sodium chloride. Yes? Okay. So then, when I talk about lattice energy, again, is the relationship between the gaseous ions and then what happens when the ions come together to form a solid, right, or are separated, whichever the case may be. So we would start with our constituent elements, right? We would then vaporize, that's what this is saying, right? We would vaporize my sodium, because I go from solid to gas, right? We would then, what are we doing now? Right, what changed was we broke the bond of my Cl2 and turned them into Cl atoms instead of chlorine molecules, right? We went from Cl2 molecules to Cl atoms, right? And then, what do we do here? Right, we ionized my sodium, right? And all of those are energy in processes, right? Which is what your book is trying to tell you, right? In that when we look at what is possible for the formation of an ionic compound in terms of what type of charge it's going to form, how many of each ion are going to come together, it's always going to be a balance between the endo processes, right, and the overall energy that can be recovered from the exo processes, right, in that the exo processes need to outweigh the endo processes, right, and that's basically what all bonding is about. And so if we look at the exo side, right, we'll see that the addition of an electron to that chlorine ion is an exothermic step. And then obviously the coming together of those respective ions is an exothermic step. And this is just known as a Born-Haber cycle, where we can analyze all the respective energies. And it's sort of a visual way to talk about Hess's law, right? Because that's all we're really doing here. Yes? Does that make sense? Note the symbolism here, right, in that this energy is the heat of formation of gaseous sodium, right, from solid sodium, right? Right here, right? This is the heat of formation of chlorine atoms from chlorine molecules, right? This is ionization energy, right? This is electron affinity. And so hypothetically, one could just be given a table full of different data values, and you should be able to put those together to come up with what the overall lattice energy might be for a substance.